our discussion of instantons in quantum mechanics before moving on to some applications to field theory in the second part of lecture. So I'd just like to recap where we were. So we were studying the double well potential. So a potential that looked something like this, just in one-dimensional quantum mechanics, had symmetric and had two minima that were both at 0, at plus and minus a. And we found there was a one instanton solution. It looked like this. And an n instanton solution. And widely separated instantons. So it will look something like this. And so we were trying to compute the transition element a e to the minus t over h bar minus a. Okay, so we wrote down an expression for the saddle point contributions from the one instanton solution. So now we need to do the same thing for the n instanton solutions. So first of all, we can note that the action of the n instanton solution should be n times the action of the one instanton solution. And we can justify this because when the x is sitting in one of the minima at plus or minus a, the potential energy is 0. And so is the time derivative. It's just sitting there as a constant. So the Euclidean action is just 1/2 x dot squared plus v. So that's approximately 0, except for the region where the particle tunnels from minus a to a or from a to minus a. So most of the contribution to the Euclidean action comes from these small regions. And so we should just get that the action of this solution with n total instantons and anti-instantons is just n times the action of the one instanton solution. So we'll get a factor of e to the minus ns over h bar, that at the end. We also have a normalization, which should be the same as the normalization we found for the harmonic oscillator. Because the potential looks like a harmonic oscillator at both of the minima. And except for small intervals, our solution is the same as the solution we found in the harmonic oscillator, which was just a constant solution sitting at the minimum. So the prefactor here should be the same as the prefactor for the harmonic oscillator, and we should get a multiplicative correction every time we have an instant time. So it should be the n times the determinant should be c times k to the n, where kn is some multiplicative correction to this formula we had for the harmonic oscillator. That involves the determinant of S double prime. And then just like for the one instanton solution, we had to integrate over the locations of the center of the instanton. We also have to integrate over the locations of the center of the n instantons over here. And I'll just allow them to be anywhere. So we said our approximations only make sense if they're well separated, but I'm just going to integrate over all possible locations of the centers of the instantons. And we'll check to make sure that at the end, that most of our contribution comes from the region where they are well separated. Finally, we have to end up at A. So we have to have one more instanton than anti-instanton if we're interested in this transition. So we should have only sum over n odd. So this is our final expression for, well, we can simplify this, but this includes all of the effects we've talked about, so that we've now found all of the saddle points that contribute to the path integral. And all that's left to do is evaluate this. So we can simplify this because S naught is independent of t. This is just an integral we can do. And if we evaluate that integral, we get t to the n over n factorial. So this just gives us a sinh. Evaluate the sum. It would be an exponential sum if we weren't missing some terms, but because we're missing some terms, we get the difference of two exponentials. Which we can define as b, a minus b. Okay. And by symmetry, this is the same thing as the transition from A to minus A. Similarly, we can compute the transition amplitude from A to A, or minus A to minus A, and it's almost the same derivation. The only difference is that we should sum over and even. We need to end up back where we started instead of in the other place. So we get the same sum just for n even. Which will be a plus b. We'll get the, instead of the difference of those exponentials, we'll get the sum. Gosh. Okay. So in order to find the energy eigenvalues, we need to diagonalize. So A and minus A are not energy eigenstates. And that's, you can find the energy eigenvalues by just computing this determinant. Which tells us that lambda is A minus B plus or minus A plus B plus minus square root of A minus B squared, which gives us either 2A or 2B. So the lowest energy levels are going to be the limit t goes to infinity of h bar over t times the log of these amplitudes, which is either 2a or 2b, which is 1/2 h bar omega plus or minus h bar k e to the minus s naught over h bar. And we could find the eigenstates corresponding to these eigenstates. Will be plus or minus 1/√2 a minus plus minus a. So the two lowest lying energy eigenstates are just the even and odd combinations of the harmonic oscillator states centered in each of the two wells. And the spatially even one has a lower energy. And so we found the energy levels and the energy splitting. You might object to this formula because well, we've computed an exponentially small correction to the energy levels, but we haven't computed the order h bar squared corrections, which in principle should be there. And will be there, but what we have computed is the leading contribution to the energy splitting. So order h bar corrections to the energy will, if we assume, as we did, that the potential is even, will correct the energy of the plus and minus states by the same amount. And what we've really computed is the leading contribution to the energy splitting. So this is dominated by instantons. And most often that's true. Instantons and non-perturbative effects in general are usually most important when there are no perturbative corrections. to the quantity of interest. So in this case, there are no perturbative corrections to the energy splitting between these two energy eigenstates. If we just use perturbation theory, we'd find delta E is 0 at any order in H bar. Okay, so one other thing we need to check here is, so we found that the n instanton solutions were saddle points, as long as they were well separated. So is the dilute gas approximation valid? Because in our expression at the top of this board, we integrated over all the possible locations of the centers of the instantons, including when they're very close. So to check this, we can note that what we were summing was a series that was like x to the n over n factorial. So the terms in this series grow until x is about n, and then decrease rapidly. So the most important terms in this sum will be the ones with x less than or equal to n. So for us, we were summing kt e to the minus s naught over h bar to the n over n factorial. So the most important terms are those with n less than or equal to kt e to the minus s naught over h bar, which tells us that n over t is exponentially small. So the density of instantons, the important contribution comes from configurations where the density of instantons is exponentially small. And we, for the semi-classical approximation to be good, we need to assume that S naught is large compared to H bar. So we're treating H bar as 1 over H bar as a large parameter. Okay. So that's our first application of instantons. And there's a closely related problem in quantum mechanics that we can apply the methods we just learned to that will turn out to have a very close analog tomorrow when we study the vacuum states of non-abelian gauge theory. So I just want to go through one more example in quantum mechanics before we turn to quantum field theory. And the last example we'll look at is the periodic potential. Where we'll look at a potential that has minima at all of the integers. And so the analysis we did for the double well potential carries over with just a few minor changes to this problem. So the major difference here is that the particle can tunnel from any minimum to any other minimum. And so if we have n instantons, and n bar anti-instantons, n minus n bar will tell us how far the particle has tunneled. And so we can basically directly write down the amplitude to go from x equals L, or to x equals L from x equals k. So we have the same prefactor. And then sum over instantons and anti-instantons. And so we have an expression like this. I'm missing one factor. Can anyone tell me what it is? So if I start at x equals k, how do I know that I end up at x equals L? So each instanton moves us to the right by 1. Each anti-instanton moves us to the left by 1. So are we allowed to have any number of?
No.
No? So how do we fix this?
And you got delta n plus n bar equals L minus k or something like that.
Right. So delta n minus n bar with L minus k. So it's a Kronecker delta. Otherwise, this formula looks very similar to the one we had before. We just have a double sum with this constraint. And we can simplify this using delta AB is integral theta over 2 pi. Theta A minus B, which is so that gives us the prefactor stays the same. Integral and with the other part of the exponential inside the sum. And so now this factorizes. We can separate all the terms that depend. We can write all this as an expression that only depends on n times an expression that depends on n bar, and do the sums independently. And so this becomes e to the kt, e to the minus s naught over h bar, e to the I theta, times e to the kt, e to the minus s naught over h bar, e to the minus I theta. So we get the plus I theta from doing the sum over n, and the minus from doing the sum over n bar, which can just be written as the exponential of 2 kt cosine theta e to the minus s naught over h bar. So we see that there are a continuum of energy eigenstates indexed by, or labeled by theta. So the energy eigenstates will have eigenvalues E theta, which is a half h bar omega plus 2 h bar k cosine theta e to the minus s over h bar. And we'll find something very similar tomorrow when we look at non-abelian gauge theory. Okay. So we're just about ready to move on to field theory. I just want to make a couple of comments about a metastable state in quantum mechanics. So we can apply these methods to a metastable state in quantum mechanics. And so what we can do is we can compute the imaginary part of the energy of the ground state, or the would-be ground state if we ignored this part of the potential. So there's some state that's localized over here that has a small imaginary part to its energy because this state is not stable. And we can find that imaginary part, which is related to the decay rate, by finding the saddle points to the Euclidean path integral. And so again, we would want to look at, just like we did for the harmonic oscillator, we could try to compute the amplitude xi e to the minus ht over h bar xi. In order to find this, we need to find the solutions to the Euclidean equations of motion with the boundary conditions that xi at our initial time is xi and is also equal to xi at our final time. So we're looking for solutions to the Euclidean equations of motion that start and end at xi. And there'll be a solution that goes from xi to x star and bounces back. There'll be a zero energy solution that goes.
So you compute E of theta, so the ground state energy is like when you sum over all the theta? Or
The ground state energy will be the one where cosine of theta is -1. So theta can go from.
Didn't we say that the ground state is just like the logarithm of the partition function? So you have like the integral, why don't you have it there?
Yeah, so the lowest energy state will be the state where theta is pi. But there's a continuum of energy eigenstates.
Yeah, but I don't understand why did you remove the integral?
So before, in the double well potential, we had just a sum of two terms. So there were two energy eigenstates. We had an exponential of something times t, or t times, exponential of t times something. But there were two separate terms, which meant there were two different energy eigenstates. Here we've got a continuum. There are infinitely many energy eigenstates. And so, well, without considering tunneling, you might expect that there are a countably infinite set of degenerate ground states. Classically, there are. So the particle could sit at any one of the countably infinite number of ground states. And linear combinations of those will be the energy eigenstates. So tunneling means that these the classical ground state become mixed up when we try to find the quantum ground state. I'll say a little bit more about this tomorrow when we go through the analog of this in non-abelian gauge theory. Okay, so we want to find a solution that starts at xi and ends at xi, and there's a zero energy solution, which just goes to x star and bounces back. So this is known as the bounce. And the only difference really between this case and the cases we've been considering before is that k will be imaginary. There'll be one negative eigenvalue. Of the operator whose determinant we need to find. So k is proportional to the square root of the determinant of s, so it'll be imaginary. And so the decay rate is related to the imaginary part of the energy, and can show that by summing over any number of bounces, we get the decay rate is absolute value of k times e to the minus se of this bounce solution. Okay, so almost the same result applies in quantum mechanics in more than one dimension. essentially the same derivation gives gamma is a e to the minus b over h bar, where b is the Euclidean action, again, of a bound solution, but this time in more than one dimension. So still want to find solutions. If there were more than one dimension, basically everything I said would still apply. We still want to find solutions to the Euclidean equation of motion in order to find saddle points of the Euclidean path integral. And those solutions would just be multidimensional. So the formula for the Euclidean action will change, but not much else. And so that basically tells us how to apply this formalism to scalar field theory. So we can think of scalar field theory as an infinite dimensional limit of quantum mechanics. And so if we're interested in a theory with a Euclidean Lagrangian, just has a canonical kinetic term and some potential, where the potential has a local minimum and a global minimum, and let's call the field value at the local minimum phi f, and field value at the global minimum phi t. So this stands for the global minimum is sometimes called the true vacuum, and the local minimum is called the false vacuum. Okay, so in field theory, this is the field configuration where phi is equal to phi f everywhere is unstable, and this configuration will decay by the nucleation of a bubble to a field configuration where phi is equal to phi true, at least in part of space. Or inside the bubble. So what changes? So first of all, what we're interested in computing is not the decay rate per unit volume. This is the sensible thing to calculate in a field theory. If we just calculated a decay rate, space is infinite, so we would get nonsensical infinite answers regardless of what that decay rate was. And it just takes the same form as before, where B is the Euclidean action of the bound solution and if we want to make an analogy back to what we've done before, we should really think about these two terms as analogous to like the potential in the quantum mechanics problem. So there are two sources of potential energy. One is just the scalar potential. The other is a gradient energy. And our boundary conditions should be that the limit as TE goes to plus or minus infinity for bound solution should be phi bar equal to phi f. This is exactly analogous to the boundary conditions we imposed in quantum mechanics, where we could compute the corrections to the energy of a metastable state by looking at the amplitude to go from the minimum to back to the minimum. So here our metastable state is where phi is equal to phi f everywhere. We should also impose the boundary condition that the limit as x goes to infinity of phi bar is phi f. So x goes to spatial infinity. And this is because we want the action to be finite. So we're doing a semi-classical approximation to the Euclidean path integral. And if we choose a configuration with infinite action as the center point of our Gaussian integral, we'll just get 0. That's not to say that infinite action configurations aren't important in the path integral. Most field configurations have infinite action. It's a set of measure 0 that have finite action, but if we want to do a semi-classical approximation, we should choose a finite action configuration as the center point of our as our saddle point. This is for finite action. And it can be shown.
So, we are working with the processing which I stay in false vacuum, and we just want to see how that decays, right?
That's right.
That's why we take minus infinity and plus infinity to stay there, like they
To stay there. So we'll find that there's an imaginary part. Well, if we go through the same calculation, there's an imaginary part to the energy of the state that sits there for all time.
And if we wanted to calculate like from phi f to phi I to phi true, we would get an exponential. Now, I mean, like the probability of going there goes to 1
Right.
with time.
It would go to 1 with time. So calculating that transition amplitude directly is, in most cases, difficult to do. So in quantum mechanics, the way you would calculate that is by solving the Schrödinger equation. In quantum field theory, the Schrödinger equation has a functional analog, the functional Schrödinger equation, but it's a functional equation, which is generally very difficult to solve. If your problem has a lot of symmetry, you can do it, and sometimes it's possible to check these instant methods using functional Schrödinger methods. But for the most part, that's much more difficult to do. So it can be proven that the solution to the Euclidean equations in motion with these boundary conditions with the lowest action is O4 invariant. So that means it should be a function only of the Euclidean radius. And so that greatly simplifies the problem. Instead of having to solve Euclidean equations of motion that depend on 4 variables, we just have to solve a differential equation that's a function of a single variable. And the equations of motion then become d squared phi d rho squared plus 3 over rho d phi d rho u prime phi. And so this is just the equation of motion of a particle moving in a potential minus u. With a time-dependent damping force. So this term here looks like a damping force. Its coefficient is 3 over rho. So if we think of rho as our time parameter, then the damping force is time-dependent. And these boundary conditions just become the limit as rho goes to infinity of phi bar of rho is phi f. And if we want a solution to be non-singular, we should also check that at the origin d phi bar d rho is 0. Okay. So that's the equation we want to solve. And it's not a difficult equation to solve for most potentials, except for our boundary conditions are somewhat unusual. We're imposing a boundary condition at infinity, and then only a condition on the derivative at 0. But we can show that a solution always exists. So this is the problem we're trying to solve. We're trying to solve for, again, thinking of rho as a time parameter, and the field value as the position of a particle. We're trying to solve for a particle that ends up at phi f equals infinity, at rho equals infinity, and it starts somewhere. We don't have any constraints on where the particle begins at t equals 0. We just know it starts at rest. So it starts somewhere over here, presumably, so that at rest. And let's call this position phi star. So a solution always exists. And we can see this by considering what happens if we start the particle at rest at different positions over here and seeing where it ends up. So it's easy to construct an undershooting solution. So if we start to the left of phi star, then we don't have enough energy to reach phi f. So this solution will end up somewhere, presumably at the minimum, to the right of phi f as as rho goes to infinity. There's also an overshooting solution. If we start, so here's phi t. If we start near phi t, we start very close to phi t. We can the slope is is 0 at phi t, so we start very close. We can make the slope as small as we like and stay there for an arbitrary long time. Our damping force is time dependent, and it decreases as rho increases, as our time parameter increases. So if we stay here long enough, we can wait until the damping force becomes negligible, and then we'll have a lot more energy than we need to get to phi f, and so we'll just fly over the barrier and go too far. And by continuity, there must be a solution in between that satisfies the boundary conditions. Okay. So there's always some solution that works. And so finding it in general is difficult, but there's one limit in which we can say something about what it looks like analytically. That's the so-called thin wall limit. And so if V of phi true is very close to V of phi f, then the solution will we'll have to stay near phi true for a very long time to make the damping force very, very small. So our potential will look like this. Just small difference. So we'll have to stay here for a very long time to wait for the damping force to get very small and then cross through the valley very quickly. So the solution will look something like this as a function of rho, where here this is phi true, which is approximately phi star, and this is phi f. So if we have a solution that looks like this, we can find the Euclidean action without very much difficulty.
Can you repeat why is staying on the top of, well, on phi plus reduces the damping?
So our damping term is this term here, this 3 over rho, d phi d rho.
Yeah.
And so we're thinking about rho as like a time.
Yeah.
So as time increases,
Oh.
the damping term decreases.
Okay.
So if we stay and the damping term is proportional to the velocity. Mm-hmm. It's d rho, d phi d rho. So if we stay here with very small velocity for a very long time, we can make the damping term as small as we like. And we're going to have to make it quite small if we only have a tiny amount of energy to spare. So the Euclidean action in this case takes a particularly simple form. So Euclidean action of this region out here, where phi equals phi f, is 0. It's approximately, because the potential is 0 when phi equals phi f, and the gradient and time derivative are 0 also. So it's 0 out here. Inside this region, so where phi is approximately right true, the only term that contributes to the Euclidean action is the energy. And so the contribution to the Euclidean action will just be the volume times the energy density difference between the true and false vacuum, which is just, so the volume of that region is just the volume of a four-dimensional ball is this. Here it is R naught times the energy density difference. And then we'll get a term, a contribution from the wall. And that should scale as the surface area. So 2 pi r naught cubed times some tension. So the gradient energy will be important, or the gradient terms will be given an important contribution to the Euclidean action in this region. And you can show that this will be the tension. Okay, so we want this to be a stationary point, a saddle point of our path integral, which means that it should be stationary under variations of r. So we should have ds d r naught is 0, which tells us minus 2 pi squared r naught cubed epsilon plus 6 pi squared r naught squared sigma should be 0. Which we can solve easily for R naught. This gives us R naught is 3 sigma or epsilon. And Euclidean action 27 pi squared over 2 epsilon cubed. Okay, so from this we can find the exponent in our decay rate formula, which is here. So we've now determined B. Finding A is more challenging. It involves computing the functional determinants around the solution, which can be done in some cases, but requires a lot of effort. But for for most cases, we often don't even care about A. We can estimate it based on dimensional analysis. And if B is a moderately large number, it often doesn't matter so much what the prefactor A is. So we can now estimate the decay rate per unit volume, or the nucleation rate per unit volume of bubbles of true vacuum. So what these solutions will look like when they're nucleated is there'll be some region outside of which the field is in the configuration phi equals phi f, inside of which field has the value phi equals phi true, and there's some wall separating the two. So this is, for instance, one of the coordinates and another coordinate. And so another question we can ask is, what will these solutions look like after they nucleate? And so it's very easy. What will they do after they nucleate? And the easiest way to figure that out is just by making Wick rotation. So if we take TE 2 minus IT, after they're nucleated, our O4 symmetry will become an O3-1 symmetry. And the real-time position of the wall will evolve as it'll be square root of T squared plus the size when it nucleates. And so we see from this equation that the wall, the bubble always expands, and the speed of the wall very rapidly approaches the speed of light on time. So once T is greater than about R naught, the bubble wall will be moving at a speed very close to 1. So if we sketch what RT will look like, T versus R of T, it will be nucleated with some finite radius and rapidly expand at a speed approaching the speed of light. And so using this formula, we can figure out things like we can figure out the decay rate of metastable states. So recent measurements suggest that so we do know of a scalar field, the Higgs field, and recent measurements suggest that the Higgs potential we might be living in a metastable state too. But as long as the decay rate is sufficiently slow, it's not a cause of concern. So tomorrow we'll move on and see another application of instantons to non-abelian gauge theories. We'll discuss the vacuum. Any questions? All right, so I'll see you this afternoon.